All right, so we've all heard the story, right? Isaac Newton, he's under a tree, an apple falls, and bam, he discovers gravity. It's maybe the most famous story in all of science. But here's the thing, the real story, the part that's truly mind-blowing, isn't about discovering that stuff falls. It's about the question he asked right after, a question that would completely change how we see the entire universe. And this is really the starting point. After seeing that apple drop, Newton apparently looked up at the moon and asked this question that sounds kind of crazy. Does the moon also fall? Now, he wasn't asking if it was going to come crashing down on us. He was wondering if the very same force that pulled that apple to the ground was also, at that exact moment, pulling on the moon. And that, right there, is the crucial bit. I mean, people have known that things fall since, well, forever. Newton's real genius was this incredible leap of imagination, to even suggest that the familiar tug we feel right here on the ground could reach out hundreds of thousands of miles into the silent blackness of space to grab the moon and hold it in its orbit.
To really get how wild this idea was, you've got to understand what everybody, and I mean everybody, believed back then. They didn't think of the universe as one big, unified place. Nope, they thought it was split into two completely separate realms, and each one had its own set of rules that were totally different.
This really lays out how incompatible those two worlds were supposed to be. Down here on Earth, the terrestrial realm, everything was considered imperfect, temporary. Heavy things just fell down. That's what they did. But up there, the heavens were a whole other story. The planets and the moon were these perfect, flawless spheres made of some mysterious heavenly stuff they called ether. And they didn't fall. They moved in perfect, divine circles, forever.
So this was Newton's challenge to that entire picture of the cosmos. He dared to ask, what if there aren't two sets of rules? What if the force yanking on the apple is the exact same force tugging on the moon? What if that force just keeps going, getting weaker and weaker the farther out you go, but never actually stopping?
Okay, so how do you prove that something orbiting way up in the sky is actually falling? It's not like you can do a hands-on experiment. So instead, Newton came up with one of the most brilliant and beautiful thought experiments in the history of science. It was a way to perfectly visualize how a falling object and an orbiting object are really the same thing.
So just imagine a huge cannon on top of a mountain so tall it pokes out of the atmosphere. If you just drop a cannonball, it falls straight down, right? Simple enough. Now fire it, but not too fast. It flies in an arc and lands somewhere over there. Okay, now fire it way faster. It travels much, much farther before it finally hits the ground. Newton's big insight was this. What if you could fire it at the perfect speed? It would still be falling toward the Earth, but it would be moving sideways so fast that the Earth would curve away beneath it at the exact same rate.
And that is the big aha moment. An orbit isn't some mystical heavenly motion. It's just falling. It's a state of continuous freefall, where you have just enough sideways speed to constantly miss the ground you're falling towards.
So, what's the answer to Newton's big question? A resounding yes. The moon is falling. It's falling toward the Earth right now, this very second, pulled by the very same gravity as that apple. It just happens to have enough sideways momentum to miss us every single time. But look, a clever thought experiment is one thing. This is physics. You need proof, you need numbers. And this is where Newton's true genius shines. Because he didn't just have this cool idea, he actually did the math to prove, with incredible precision, that the force on the apple and the force on the moon were one and the same.
So the first key piece of this puzzle was the distance. Newton knew that the moon is about 60 times farther away from the center of the Earth than an apple on its surface. Just hang on to that number for a second. 60.
Okay, next up, he needed a rule for how gravity gets weaker. He pictured it spreading out from a point, kind of like the light from a candle. The farther away you get, the more that light spreads out and the dimmer or weaker it gets. He figured gravity worked the same way, specifically that it gets weaker with the square of the distance. So if you go twice as far away, the force is 4 times weaker.
So let's put that idea to the test. If the moon is 60 times farther away than the apple, and gravity follows this inverse square law, just how much weaker should the Earth's gravitational pull be way out there where the moon is?
Well, the math is pretty simple. If it's 60 times farther, the force of gravity should be 60 squared, or 60 times 60 weaker. And that comes out to 3,600. So his theory predicted that gravity at the moon's distance is 1/3600th as strong as it is here on the surface. That's a very specific, testable number.
And this is where it all clicks together, just beautifully. On one side, you have his theory predicting that gravity out there should be 1/3600th as strong. On the other side, you have the actual observable universe. Newton calculated how far the moon actually falls, meaning how much its path deviates from a straight line every second. And the result? It was exactly 1/3600th the rate an apple falls on Earth. The prediction and the observation were a perfect match. The proof was undeniable.
Now, this was so much more than just a clever calculation. You could argue this was the single greatest moment of unification in the history of science. With one idea, Newton tore down that ancient wall between the Earth and the heavens. There weren't two separate worlds with two sets of rules anymore. There was just one universe.
He boiled this entire grand idea down into one single elegant equation, the law of universal gravitation. All it says is that the force of gravity between any two things in the universe depends only on how massive they are and how far apart they are. That's it. One simple rule that applies to everything, everywhere.
And the impact of that one little equation was just staggering. It completely unified our view of the cosmos. The exact same law that makes an apple drop from a branch is what choreographs the beautiful dance of the planets around the sun, and it even shapes the majestic spiral arms of galaxies billions of light years away. It all follows the same rule.
And that's really the biggest lesson from all of this. What Newton showed us is that the universe isn't arbitrary. Nature doesn't have one rule book for here and another one for way out there. The laws of physics we discover in our own backyard are the same laws that operate in the deepest, darkest corners of space.
So from a simple falling apple to the moon in the sky, Newton showed us that we are all, quite literally, dancing to the exact same cosmic tune. And it leaves you with this incredible, profound question. What other universal laws are still out there just waiting for the next curious person to find them?